Welcome to Descriptive Statistics. Today, we are going to explore the absolute foundation of all modern statistics, the relationship between a statistical population and a sample. If you have ever wondered how we can predict an election without asking every single voter or test the quality of factory products without destroying all of them, you are in the right place. Let us dive in. To understand these terms, imagine you are cooking a massive pot of soup. To check if it has enough salt, you do not drink the entire pot. You stir it and taste one spoonful. In statistics, that entire pot is the population, represented by capital N. It is the complete set of everything you want to study. The single spoonful is the sample, represented by lowercase n. We use samples because checking every single item is often impossible, too expensive, or takes too much time. By looking at a small, well-chosen piece, we can learn the truth about the massive whole. Now that we know what a population is, let us look at how we mathematically represent its average. This is the population mean formula. The Greek letter mu represents this true, exact average of everyone or everything in the group. To find it, we take each individual value, represented by capital X sub I, and sum them all up. Then we divide by the total population size, capital N. However, as n gets massive, calculating mu becomes practically impossible in real life. You cannot measure the height of every single person in a country. That is exactly why we need samples. Because we usually cannot calculate the population mean, we calculate the sample mean instead. Here, the symbol x bar represents the sample mean. Instead of measuring everything, we only add up the values in a small sample, represented by lowercase x sub I. We then divide that sum by our sample size, lowercase n. If our sample is chosen fairly, x bar will be very close to mu. If the sample size n increases, our estimate generally becomes even more accurate. Let us see this formula in action with a concrete example. Imagine a factory produces 10,000 light bulbs every day. The manager wants to know the average lifespan. Testing a bulb destroys it, so we cannot test all 10,000. Instead, the manager randomly selects a sample of 5 bulbs. Their lifespans are 1000, 1020, 980, 1010 and 990 hours. We start with our sample mean formula, which will act as our blueprint to combine these individual measurements. Continuing with our calculation, we substitute the individual lifespans of the 5 tested light bulbs into the numerator of our equation. At the same time, we place our sample size of 5 into the denominator. Next, we add the 5 values in the numerator together. This addition gives us a total sum of 5,000 hours for the entire sample. We keep the denominator exactly the same for now. We are now ready to find the final average. Finally, dividing 5,000 by 5 gives us a final sample mean of 1,000 hours. Because we selected the bulbs randomly, this sample is unbiased. Therefore, the manager can confidently estimate that the true population mean for all 10,000 bulbs is approximately 1,000 hours. We achieved this valuable insight without having to destroy the entire batch of products. Now that we have calculated a sample mean, we must understand that populations come in two main types, finite and infinite. A finite population is one where you can actually count every single member, like the exact number of registered voters on a list. An infinite population is theoretical and has no end, like the continuous output of a factory machine running forever, or flipping a coin infinitely. This distinction matters. For a finite population, taking out a sample changes the probabilities for the remaining items, much like drawing cards from a deck without putting them back. For any sample to be useful, it must perfectly represent the population, just like a well-stirred pot of soup. When it fails to do this, we call it sampling bias. There are 3 major types you must know. First is selection bias, like surveying average income but only asking people at a luxury mall. Second is non-response bias, which happens when people who ignore a survey are fundamentally different from those who answer it, like angry customers leaving restaurant reviews. Third is survivorship bias, where we only look at things that survived a process, like engineers in World War II who only studied the airplanes that returned, ignoring the ones that were shot down. Let us look at this visually. On the screen, the large circle represents our entire population. The unbiased sample in the center captures a true random mix of the population, giving us an accurate picture. However, look at the biased sample on the edge. It only captures one specific type of data, completely missing the diversity of the whole group. If you use a biased sample, your mathematical calculations might be flawless, but your conclusions will be completely wrong. Always ensure your sample is well stirred. Understanding bias is crucial when we want to predict outcomes for massive groups, like a whole city or country. In polling, we do not just want an average. We want to know how many people will take a specific action, like voting for a candidate. To do this, we first find the fraction of people in our small sample who support the candidate. This is called the sample proportion. Once we have this small-scale fraction, we can scale it up to the size of the real world to estimate the total population behavior. This brings us to the formula for the sample proportion. Conceptually, it is just a simple ratio, but it is the foundation of polling mathematics. The lowercase letter p represents the sample proportion. The variable x stands for the number of successes, which means the number of people who gave the answer we are looking for. We divide this by lowercase n, which is our total sample size. If the number of successes x increases, our proportion p gets closer to 1. If nobody supports the candidate, p becomes 0. Once we have our sample proportion, we use this second formula to calculate the expected total in the entire population. We denote this expected total with the capital letter E. To find it, we simply multiply our sample proportion, P, by the total population size, capital N. This multiplication scales our small sample finding up to the actual size of the city or country. Let us look at a real-world polling example to see how these two formulas work together. Here is our scenario. A city has a finite population of 1,00,000 registered voters. A polling agency wants to predict the upcoming mayoral election, so they randomly call 400 voters. Out of those called, 240 voters say they will vote for candidate A. We need to calculate the sample proportion first. We start with our proportion formula. P equals x divided by n to find the fraction of support within our small survey. Continuing our calculation, we substitute 240 into the top of the fraction. This is the count of voters who expressed support for our candidate. We then substitute our sample size of 400 into the bottom. Dividing the numerator by the denominator gives us a decimal value of 0.60. In everyday language, this means 60% of the sampled voters support candidate A. This percentage is our best guess for the current mood of the electorate. Now that we have our sample proportion of 0.60, we can calculate the expected total votes in the entire population. We bring in our expected total formula, E equals P times N. We plug in our calculated proportion and we insert the finite population size of 100,000 registered voters. This crucial step connects our small survey data directly to the actual size of the city. We are now ready to compute the final prediction. Multiplying these together, the polling agency estimates that candidate A will receive a total of 60,000 votes. However, because this is a sample and not the whole population, there is always a margin of error. If the polling agency accidentally called only wealthy neighborhoods, this estimate would suffer from selection bias, and the 60% estimate would be completely wrong for the whole city. But assuming a fair sample, 60,000 is our best scientific prediction. We have covered a lot of ground today. Remember, the population is the entire group you want to study, while the sample is the small piece you actually measure. We use tools like the sample mean and sample proportion to make highly educated guesses about the massive whole. As long as we avoid sampling bias and pick our sample randomly, this small piece will accurately reflect reality. This simple but powerful concept is what makes all modern scientific research possible. Great job following along.